Okay, I'm going to go over problem number 2 on worksheet 4. We talked about it in class briefly, how the voltage doesn't change, but as I looked at this problem more carefully, it's not asking about what happens to the potential difference between the plates. It's asking about the amount of charge on the plates. What happens to that as the two plates are separated? Since this is a 6-volt battery, and we've got a distance, let's just call it D, between these two guys right here. If you actually separate these two plates further, so let's say this positive plate is pulled further over this way, so now you've got, let's just call it a distance D prime further away. Since they're opposite charges, you have to do work to separate those two. So you are pushing them further apart. And so what ends up happening is, because you've got a relationship between potential and the E field that looks like this, you've kept this the same because it's connected to a set source of potential difference, a battery, so that's not going to change no matter how far apart the plates are, but you've increased the denominator, which is our D. This is now D prime, so this is bigger. So your E field is actually going to be smaller. So the forces exerted on these charges on opposite sides is less. So what happens is the work that you do in separating them, actually some of the charge is pushed back into the battery because there's less attractive force between those two plates. So you end up having less charge on the plates because of the decreased E field and the smaller attraction between the two plates because of the greater distance apart. Okay, so Q goes down. Potential difference is the same. So I just wanted to make sure we were clear on that one. Okay, now we're going to look at number 7, which is asking about the potential distance, certain distance away from a point charge. And they mentioned that the electric potential an infinite distance away is going to be 0 volts, which is kind of the custom. So you've got this point charge right here of positive 8 microcoulombs. You guys remember what that is now, right, from the last test? And we're a distance of 0.40 meters away in space. Okay, so we're just asking, at this point in space, there's not a charge there, but what is the magnitude of the potential at that point? If 0 is an infinite distance away, the potential at this point can just be found by using the equation for a point charge. So the potential at 0.4 is KQ over R. So pretty straightforward. Most people got this right. I'm just showing you this so I can get to part C, and you understand where the numbers came from when we get to C. Okay, and this is 1.8 times 10 to the 5th. You could either say joules per coulomb, or you could say volts. Okay, so 180,000 volts at a distance of 0.4 meters with a charge of 8 microcoulombs. Okay, so this next part asks about if a 2.2 nanocoulomb charged plastic sphere is moved from an infinite distance away to 0.4 meters away from that positive 8 microcoulomb charge. What's the change in the energy of the system? So infinitely away, it's 0. So you're now moving it to be a distance of 0.4 meters away. So you've got this charge that far away, and this is a small charge. This is 2.2 nanocoulombs. That's 10 to the negative 9th. So you want to find the electric potential. The change in potential energy is final minus initial. Initial was 0. Final is going to be K, and they are both positively charged. So we're going to have 2.2. I'm going to move this over so I can fit it all on one line. It's going to be equal to 9 times 10 to the ninth, 2.2 times 10 to the negative ninth, and 8 times 10 to the negative sixth over the distance between them is 0.4, and I think we get, so the answer is going to be 3.96 times 10 to the negative fourth joules. But you'll notice we could have done it a different way too, because the terms here, K original Q divided by R, that's just the potential. So delta UQ, if you remember, is also equal to K times the change in potential. I'm sorry, not K, Q times the change in potential. Because the definition of potential difference is the change in energy divided per unit charge. Okay, that's how we originally defined potential difference. So you could have done the same exact problem just by multiplying the 2.2 nanocoulomb charge by the 180,000 volt potential change from 0 at an infinite distance to 180,000 at a distance of 0.4 meters away, and multiply it by 2.2 nanocoulombs. It's going to give you exactly the same answer. Okay, let's move on to part C. Okay, for part C now, you've got a 1 kilogram charged plastic sphere released from rest. How fast will it be traveling after it moves 0.5 meters in a straight line radially away from the point charge? We assume we're at that same 0.4 meter distance to start with. So we've got this 8 microcoulomb charge right here. We've got this tiny sphere that is 1 gram, and it is 2.2 nanocoulombs of charge. Not very easy to write that small on this software or this app. So it starts out 0.4 meters away, and it's going to end up another greater distance, 0.5 meters away. Okay, so this is the final potential out here. This is the initial potential. Right here. And we know the initial potential, we already know this, is 1.8 times 10 to the fifth. The question is, what is the VF at this point right here? What is that? So we need to figure out what the potential is at that point way out there. So we can do that pretty easily. We'll say, what is the voltage, KQ, over that new distance there, and actually I'm going to put it down here, 9 times 10 to the ninth. It's the same point charge that's causing the potential way out there. So the potential due to that point charge is 9 times 10 to the ninth times the charge, 8 times 10 to the negative sixth, over, now it's 0.9 meters away, so the sum of those two distances. So you've got a potential VF of 80,000. I guess 80 times 10 to the third, or 8.0 times 10 to the fourth. Okay, so to find out how fast this thing is going, which is what we're really trying to find here. We're not. I should have read the question a little more carefully when I started out. We're trying to find the velocity at that point. If it's moves in a straight line away, that means it's moving along the electric field lines, which means its change of potential is directly related to this equation right here. So the velocity at that point, we can use energy methods to figure that out. So we know we had all gravitation or electric potential energy to start with. So the change in the UQ plus the change in the kinetic energy is going to add up to 0 because of conservation of energy. So we know that whatever we lose in electric potential energy, we're going to gain in kinetic energy. If it starts from rest, it's released from rest, so it has 0 kinetic energy at the beginning. All of the loss of electric potential energy is going to go into kinetic energy at the end of the problem. So we start out with the UQ can be expressed in terms of the change in potential, which we just found. That's going to be equal to 1/2 mv squared. So we've got a 2.2 nanocoulomb charge, that's 10 to the negative ninth. The change in potential, it's going from, the final potential is 80,000. The initial potential was 180,000. So your change in potential is 100,000 in the negative direction. Oops. Actually, I see what I did here. This should be a plus, sorry, plus equals 0. And down here, shoot, that should be a plus equals 0. So if I know my mass is 0.001 kilograms and I solve for v squared, obviously the v term is going to move to the other side to solve for v, so the two negative signs are going to cancel out, and I get a velocity of 0.66 meters per second. So we didn't have quite enough time to finish this in class on Tuesday. I wanted to make sure we got a chance to get a chance to see the solution to it. If you have any questions, by all means, please come and see me after class or before school someday. Okay?